Again to our course on Cyber-Physical System Fundamentals. Today is the 18th lecture of our course, and today we'll continue our discussion on scheduling algorithms with classical scheduling algorithms for periodic systems. So, considering the structure of this course, we are still in the chapter 6 of the accompanying textbook, which is a chapter on mapping of applications to execution platforms. So, as you've already seen last time, in this course we consider several classes of mapping algorithms, and we are in this first class here, the class of classical scheduling algorithms, which are suited for independent tasks, which ignore communication between tasks, and which are mostly suited for monoprocessor and homogeneous multiprocessor systems. So let us consider periodic scheduling. In periodic scheduling you have independent tasks, and each of these tasks is expected to repeat at a given point in time. And each execution instance of a task is called a job. And now the question is, what is optimal scheduling for such a set of periodic tasks? The notion of optimality for aperiodic scheduling, which we've seen last time, does not actually make sense for this periodic scheduling approach here. For periodic scheduling, the best that we can do is actually to design a scheduling algorithm which will always find a schedule if such a schedule exists. So, a scheduler for periodic systems is defined to be an optimal scheduler if and only if it will find a schedule if such a schedule exists. So let's first consider the case of periodic scheduling without precedence constraints. So we start off by considering a set of tasks Ti with a given set of properties. So we start off with the period of a task Ti, so the amount of time that may pass before this task has to be repeated. Each task has a given execution time, Ci. It has a given deadline, which is a time between the point in time when it becomes available here and the point in time until it has to finish execution. Like last time, we also defined the laxity of a task, which is defined as the deadline of the task minus its computation time. And we have a finishing time of the task, which is the time Fi. So, using these parameters, let's first define an important characteristic of scheduling problems, and this characteristic is the average utilization of a system, which is usually denoted by the Greek character mu. And you calculate the average utilization by considering the amount of time each task uses a processor. So you calculate the calculation time for each task and divide it by its period time. So let's say you have a calculation time of 4 units and a period of 8 time units. So this would be 0.5, so it would use up half of your available processing time for executing that task. And then you sum up this over all of your tasks in a system here. And so we can easily derive the necessary condition to ensure that a set of tasks is schedulable on a system with m processors. So the utilization mu, the average utilization, has to be less or equal than the numbers of processors available. So for independent tasks, we can use the RateMonotonic Scheduling approach. This is the most well-known technique for scheduling independent periodic tasks and was first described by Leo in 1973. So here we make some assumptions on the set of periodic tasks that we want to schedule. First assumption is that all of the tasks that have hard deadlines are actually periodic tasks in our system, and all of the tasks in the system are independent, so no task has to wait until another task has finished to continue calculating. Another simplifying assumption is that the deadline of a task equals the period of that task for all of the tasks in our systems, and that the computation time for each iteration of a task for each job is constant, and that we know this computation time for all of the tasks. Again, another simplification is that the time required for switching context between the set of tasks is negligible. And now Leo defines that for a single processor and for n given tasks, the following equation holds for the average utilization mu. So again, we calculate mu by summing up the amount of processor time required for each task over all tasks, and now we demand that this has to be less or equal than n times the nth root of 2 minus 1. So in rate monotonic scheduling, we have to determine which task is actually being executed at which point in time. So the policy used in rate monotonic scheduling is such that the priority of a task is a monotonically decreasing function of the period of that task. So at any time, the highest priority task among all those that are actually ready for execution is then allocated. And now we can formulate a theorem here. And the theorem says that if all rate monotonic assumptions are met, we can guarantee the schedulability of the whole set of tasks. So now we can ask ourselves, what is the maximum utilization that can be present in a system to guarantee schedulability of the system when the number of tasks is increasing? So we can define the maximum utilization as a function of the number of tasks. So we know that the utilization mu is the sum here, and the postulation by Liu says that this has to be less or equal than n times the nth root of 2 minus 1. And when the number of tasks is increasing, we can calculate the limit for the number of tasks against infinity, and using some of the mathematics you should know from high school, you can determine that this limit when going to an infinite number of tasks is a natural logarithm of 2. And so when we plot our formula n times the nth root of 2 minus 1 against an increasing number of processes, you see, of course, when we only have one task, we can utilize the CPU to 100%. When we have two tasks, this value is about 0.828. And we see it's continuously decreasing, and since ln of 2 is about 0.69, this will be the limit when n goes towards infinity. So let's look at an example of a rate monotonic generated schedule here. So we have three tasks, T1 to T3. T1 has a period of 2. T2 has a period of 6, and T3 also has a period of 6. So from the policies we know that T1 has the shortest period, so it may preempt T2 and T3. T2 and T3 again have equal periods, so they will not preempt each other. So we have a rate monotonic scheduling. We start off with scheduling T1, which takes half a time unit here, and we start off scheduling T2, which is again at point in time 2 preempted by T1. T1 again has finished its computation here, so T2 can continue. Then T3 starts and gets activated, and so on. So the question is it easy to determine or to build an example case where rate monotonic scheduling can actually fail? So we consider this simple example here. We have two tasks, task 1 with a period of 5 and computation time of 3 time units. And we have a second task 2 with a period of 8 time units and also an execution time of 3 time units. So now we can start off calculating the average utilization mu here, which is 3 over 5 for task 1. It takes 3 time units out of every 5, plus 3 over 8, 3 time units out of every 8 for the second task. And this is about 0.975. Now when we consider the formula we've seen before for these two tasks, we know that this guaranteed schedulability constraint is that the maximum utilization does not exceed 2 times the square root of 2, since we have two tasks here, minus 1, and this is about 0.828. So let us have a look at the schedule here. We start off scheduling task 1 first, because it has a shorter period. So it starts executing for all of its 3 time units. Then task 2 can take over. So task 2 takes over at point in time 3 and starts executing for 2 time units. Then the period of T1 is up, so the next iteration of T1 will be started here because it has a higher priority, it has a shorter period. So again, T1 starts executing for 3 time units, and then we arrive at time unit 8. Now time unit 8 is a period for T2, and we have only executed 2 time units of T2, so we have to schedule the 3rd time unit of T2 and the next period already, and so this soon, at this point in time, we have already missed the deadline. Let's have a look at another example here. Again, we have two tasks. We have task 1 with a period of 5 and an execution time of 2. And we have task 2 with a period of 7 and an execution time of 4. So again, we can calculate the average utilization here. Mu is 2 over 5, so 2 time units out of every 5 time units for the first task, plus 4 over 7, 4 time units out of every 7 time units for the second task, which is about 0.97, so very, very close to full utilization. And again, for 2 tasks, as we've seen as a previous slide, we have the maximum utilization to guarantee schedulability, which is 0.828. So again, we start off scheduling T1 for 2 time units here. T1 has executed all of its time units. Then we can switch over to T2. So T2 will execute for 3 time units here. Then the period for T1 is again starting. So T1 takes over for 2 time units. And again, we have the case that we have to schedule the last time unit for the first iteration of T2 in its second period. So we've already missed the computations here. We have missed our deadline. Now to visualize this, we can use the tool Levy RTS, which was developed here at our institute. So Levy RTS is a system that allows to schedule or to simulate the schedule for several scheduling algorithms and for several parameters for tasks. So I've already prepared 2 tasks here. The task we've seen on the previous slide. So we have a periodic task T1 with a period of 5 and an execution time of 2. And we have the second task with a period of 7 and the execution time of 4, as we've seen on that previous slide here. So that's the 2 tasks we've defined. And using our Levy RTS tool, we can now simulate what's going on by doing a full simulation or a step-by-step simulation of the system. I'll do a step-by-step simulation so you can easily see what's going on here. So let's start off with the first cycle. Of course, we know task 1 will be scheduled because task 1 has the higher priority. So task 1 is scheduled for 1 time unit. We know it takes 2 time units per period, so it has executed half of its computation time. So let's go to the next time unit. Again, we know task 1 is still running. It has executed all of its computation time. So in the next time unit, task 2 can take over. We've seen it has executed 1 time period here. So 1 out of 4 is 25%. And again, the next one and the third one, we are 75%, 3 out of 4 time units. And now the next period for task 1 is starting. So task 1 takes over again. And you see in this tool we distinguish between different iterations by different patterns of the color. So we have these vertical stripes here and the red color for task 1 to determine that this is already the second iteration for task 1. And now task 1 can execute for 2 time units. It's finished now for its second period. And now task 2 can take over. And as you've seen here, no vertical stripes, so this is the last remaining time unit. Now it's up to 100% of task 2, but this is already executed in the second period, and only then can the second period of task 2, the second iteration, start. You see it got these stripes here, and we've already missed the deadline here. So now we can ask ourselves, why does rate monotonic scheduling actually fail? Now let's have an intuitive look at this problem. So we start off with a scheduling of T1, and T1 executes all of its time units. Then T2, the second task, may take over, but it's interrupted right in between calculating because the period of task 1 starts again and T1 takes over. Now, when T1 has finished its second period, T2 can take over again. It's still in its first period here, and it continues executing. But as it continues executing, T1 takes over again, even though T2 only has 1 time unit remaining in its period and actually could complete its calculation in that period. But since we have determined that the tasks with a smaller period actually have precedence, T2 is preempted at this point in time, and T1 takes over, causing T2 to miss its deadline. Now, such a system can only work for certain cases, and this case is if the period of the second task is equal to an integer number of times of the period of the first task. So, if we know that these meet at some point in time, the 2 deadlines, we know we can always schedule the iterations of T2 in the idle times for T1, and so If this condition holds true, the system is actually schedulable, and we'll never have that situation of cycles that hang over, even though we are still inside the deadline, but we are preempted here. So what is a critical instance in Schnitt? So what are the critical instance for rate monotonic scheduling? Let's define the critical instance first. A critical instant of a task is the time at which the release of a task will produce the largest response time for that task. So let's start off with a lemma. We will postulate that for any task, the critical instant occurs if that task is simultaneously released with all of the higher priority tasks of a system. So we can actually prove this lemma, and we start off with defining a set of n periodic tasks, and these are sorted. So for all indices I of a task, this following condition holds true, that the period of task I is less or equal than the period of task I plus 1. Schnitt. So the response time of a task Tn with a larger period is delayed by all of the tasks Ti of higher priority. So we have our task Tn with a low priority, a large period, and we have tasks Ti with lower periods, so higher priority. So whenever the period for that task, any of the tasks Ti with that higher priority starts, our lower priority task Tn is preempted, and so has to wait until the high priority tasks have finished executing. Now we can see that the delay may actually increase if the task Ti starts earlier. So if Ti starts earlier here, we interrupt Tn at an earlier point of time, then it continues executing, and then actually the next period of Ti starts again, and we see the maximum delay is actually increasing. And we can determine that the maximum delay is actually achieved if the task Tn and the task Ti of higher priority start simultaneously. So now we can repeat this argument for all of the tasks in our system from 1 to n-1, so for all higher priority tasks. And so we know that the worst case response time of a task occurs when it's released simultaneously with all the higher priority tasks, because you can just repeat it down to the task with the highest priority, and so we have actually proven this lemma. So schedulability is checked at the critical instance, and if all tasks of a set of tasks are schedulable at their critical instance, then we know they are schedulable at all release times in the system. And this observation helps to design examples where we know it works and where we know it can go wrong. Let's now consider the case we've seen before, where the period of a task I plus 1 is an integer multiple of the period of the task with one higher priority. So the next lemma is if each task period is a multiple of the period of the next higher priority tasks, then the schedulability of the system is also guaranteed as long as the processor utilization for a single processor system stays less than or equal to 1. So again, we can prove this. We assume that a schedule for task Ti is given, and then we can add Ti plus 1 to the schedule, and we see that this task Ti plus 1 fills all the idle times of Ti here, and Ti plus 1 completes in time if the accumulated amount of idle time in our system is large enough, so if the utilization is still less than or equal to 1. And again, we can use this iteratively, so for considering the next lower priority task, we can use Ti plus 1 as the higher priority task. So let's take a look at the properties of rate monotonic scheduling. Rate monotonic scheduling is based on static priorities. So this allows rate monotonic scheduling to be used in an operating system that supports these static priorities. An example for this is Windows NT. So if we know that for all of the tasks, the period of a task with a lower priority is an integer number of the period of the task with a higher priority, we do not need any idle capacity in the system. So then we can guarantee schedulability as long as the processor utilization is less than or equal to 1. Actually, we only presented one of the possible approaches to rate monotonic scheduling. You can find a huge number of variations in the literature, and you can also find a large number of formal proofs to ensure schedulability or non-schedulability of systems here. Let's take a look at earliest deadline first scheduling again. Earliest deadline first scheduling can actually also be applied to periodic scheduling. Earliest deadline first is optimal for every hyperperiod, which is the least common multiple of all of the periods in a system. So we can deduce that EDF is optimal for periodic scheduling, and now we can determine that EDF must be able to schedule the example in which rate monotonic scheduling has failed. So let's compare the two schedules for EDF and RMS. We have the example we've seen before of these two tasks T1 and T2. T1 has a period of 5 and T2 has a period of 8, and we have an execution time of 3 time units each. So we start again with rate monotonic scheduling. T1 gets executed for 3 time units. T2 starts executing and is interrupted after 2 time units. T1 takes over again, uses up the next 3 time units. We're at the beginning of the second period for T2, but still have 1 time unit left in the for execution of the first iteration, so we have missed the deadline here. So in the rate monotonic scheduling, we always give priority to the task with the shortest period. In earliest deadline first, like the name says, we of course give priority to the task with the most rapidly approaching deadline. So again, we start out with task 1, which executes for 3 time units. Then we switch over to task 2, and task 2 can now execute for all of its 3 time units, since its next deadline is at time 8, whereas the deadline for task 1 in its next period is at time 10. So here's again the difference. The third computation unit of T2 can take place, and only then we switch again to task 1, which can then execute for 3 time units because its deadline is 10, whereas the next deadline for T2 is 16, and so on and so forth. And you can see, while this schedule does not work with rate monotonic scheduling, earliest deadline first is actually able to produce a valid schedule for this problem. However, there is one drawback to using EDF for scheduling these systems, because the priorities in such a system actually change, because the priority is always assigned to that task with the earliest approaching deadline. So earliest deadline first scheduling cannot be used with an operating system that only provides static priorities to tasks. However, there might be a solution. So a rather recent paper by Marwedel and Slomka at the DATE conference in 2008 demonstrates how we can achieve that an operating system with static priorities can be extended with a plugin that provides earliest deadline first scheduling. And the key idea of this paper is that delayed tasks become ready if they shouldn't be executed under earliest deadline first scheduling. So when we compare rate monotonic scheduling and earliest deadline first Schnitt. So when we das ist doch zum Kotzen. So when we compare rate monotonic and earliest deadline first scheduling, we can see that the priorities in RMS are static, while earliest deadline first requires dynamic priorities. So rate monotonic scheduling can work with an operating system with fixed priorities, while earliest deadline first scheduling does not work. However, as we've seen in the previous slide, there might be approaches to handle this situation. Rate monotonic scheduling does not use the full computational power of a processor, because we have that limit of n times the nth root of 2 minus 1, whereas earliest deadline first can actually use all of the computational power a processor provides. And so the other way around, in earliest deadline first scheduling, it's possible to exploit the full computational power of a processor without provisioning for slack, which is not possible for rate monotonic scheduling. So if we add sporadic tasks to such a system, and these sporadic tasks were connected to interrupts, the execution time of other tasks in the system would become very unpredictable. So If we have such sporadic tasks in the system, we could try to introduce a so-called sporadic task server, which is periodically checking for ready sporadic tasks. And so, using this sporadic task server, which is executing periodically again in our system, the sporadic tasks are essentially turned into periodic tasks executing in the context of that sporadic task server. Now, when we also consider dependent tasks, the problem of deciding whether or not a schedule exists for such a set of dependent tasks and a given deadline is NP complete in general. So we can use several strategies here to solve that problem. And we can start off by adding resources so that scheduling actually becomes easier. So actually we have more possibilities, more liberty to schedule. Or we can split the problem into a static part and a dynamic part, so that we only have to take a minimum of decisions at runtime. Or we can try to use scheduling algorithms we know from high-level synthesis. So to sum up here, we've seen approaches to periodic scheduling, we've seen rate-monotonic scheduling, we've compared it to earliest deadline-first scheduling, and we've briefly talked about dependent and sporadic tasks here.